Okay, so the next thing we have to do is to try and identify what particular isotope of radiation would be most suitable for each of the kind of applications in the previous few pages. Um, we base this on two things. Firstly, we have to use the right type, either if it's alpha, beta, or gamma. And then the second thing we need to look at really is what's the half-life. Do we want something that has a very short half-life? What that means is the radiation or the activity from the source will decrease quite quickly. Okay, because we'll half and half and half and half until it's essentially zero over a short period of time. The activity will decrease. It'll be less dangerous after a short period of time. However, we might want another situation where that's not the case, where we want something that has a very long half-life. Something that has a long half-life, it will take much longer for it to half and half and half again, which means the activity doesn't decrease as quickly. It's much more constant. And there may be situations where we want things to last a long time, in which case it's better to have that longer half-life. So let's go back over the last few pages and try and select one of these isotopes for each of the possible uses. So the first one we looked at was agriculture, where we needed gamma radiation to kill the bacteria in the strawberries. Now, the key thing here is we're going to invest in a factory that has conveyor belts to irradiate these strawberries. We want this source to actually last a long time. Remember, it doesn't make the strawberries radioactive, so we don't have to have some of the short half-life, so the strawberries will be safe to eat after 10 days. The strawberries are safe to eat as soon as they come out of that conveyor belt, because the radiation just kills the bacteria. It doesn't make the strawberries radioactive. If we use something with a short half-life for our source, it would mean one day the activity will be high, the next day it will be less, the next day it will be less, the next day it will be less, and eventually it's not going to even kill that bacteria. So we want a gamma source that has a long half-life. So probably the best one we could use for this case would be the cobalt 60, which has a half-life of 5.3 years. Likewise for our smoke alarm, we want our smoke alarm to last a long time, so we need an alpha source that has a long half-life. So in this case we would use the americium 241, and that is the one that is used in smoke alarms. It has a half-life of 433 years, and we're not going to see much of a decrease over the lifetime of a house even. Likewise for our third use, where we're manufacturing the aluminium foil, we need a beater source, but this works by checking how much radiation is at the other side. If it's too thick, there'll be less radiation detected on the opposite side. For that to be true, we needed to have a very long half-life, because if this source has a short half-life, then the amount detected on the other side is going to decrease quite quickly, even if the thickness is the same. So therefore, we want it to last a long time. So in this case, we would use our cesium 137 for that application. Next one's the opposite. Okay, we're going to inject some source in at the start of the pipe. Where there's a leak, we can detect it, but somewhere at the other end, we're going to want to use this liquid again. Now, I don't know if this would be used for drinking water, because you might have to wait a very long time before it becomes totally safe for human consumption. But let's say it is oil or petrol that we're pumping through this. We will want that to be safe quite quickly. We need a gamma source, so I would say we would either use, in this case, sodium 24 or technetium 99, depending on how long we think it's going to take us to find that leak. But in this case, we'll probably opt for the shorter half-life of those, which is technetium 99. Next one, our radioactive tracers. We either needed beta or gamma source that's got quite a short half-life. If we're using beta, we'd use the magnesium 27, because it has a half-life of 10 minutes. So within an hour or two, the activity from that source is going to decrease to zero. We don't want that person constantly walking around emitting and absorbing radiation, so we need a short half-life here, short enough that it will die down quite quickly, but long enough that it gives it time to work around the human body and for the radiographer to take an image of that. If we were using gamma, once again, it depends how long it takes, but it's probably another case where we'd use as short as possible in our list, which is the technetium, which has a half-life of 2.5 hours. Isotope, mass number of 99. Sterilization of medical equipment. Same for our strawberries. We probably want to be able to sterilize equipment for a long period of time without the radiation decreasing. So we'd use the cobalt 60. Radiotherapy, this is a harder one to gauge. If we're using the external beam, we need a gamma source. If we want to use it for patient after patient after patient, we probably want something that's going to last a very long time. So in this case, we might use, what's our longest, the cobalt 60. However, if different patients need different amounts of radiation, we might need to use different samples for each patient. We might need something that's got a shorter half-life. If we're putting the alpha in, we only have two things that have very long half-lives. The gas is probably a little bit dangerous to be injecting. So out of those ones, we might use the americium. However, remember, at the end of this process, once they've done their treatment, we would have to go in and remove that source from them again.